Hey guys, this is Darshan Lokhande. I am a pre-final year BTech CSE student at IIIT Pune. Welcome to our channel Learn Competitive Programming with CodeChef. If you are interested in competitive programming and want to learn data structures and algorithms, this is the one-stop destination for you. We post weekly problem explanations and concept videos. So don't forget to subscribe to our channel by hitting that subscribe button and also the bell icon. The problem that we are going to discuss today is a special tree. The problem appeared in April 21 lunchtime and has a difficulty level of easy medium. The prerequisites to solve this problem are trees and DFS. The problem statement goes as follows. We are given a tree with n nodes that are numbered from 1 to n, and also we are given k special nodes, that is f1, f2 up to fk. So after giving this information, we are told that d p comma q is nothing but the distance between two nodes p and q, and as it is a tree, the distance is always unique. So what is the question? The question given is that we'll also be given an additional node a, and for all the nodes from 1 to n, that is b belonging to 1 to n, we have to find the maximum value of d a comma u minus d b comma u, where u is a special node. So in this diagram that you can see on the right hand side, I have drawn a sample tree where the given node A, I have considered it as my root. So you can see over here, and the nodes in blue, which you can see over here, are nothing but the special nodes. So we'll be given such a tree with the special nodes and the node A. Now for each of the following nodes, so for every node, we have to consider it as the node B and tell the maximum value of this expression. So the node A is fixed, B is belongs to 1 to n, that is for each node we have to answer the value of this expression, and u we can choose as any special node in the tree. But there is one constraint, that we have to maximize this value. This expression which I have written, that is dau minus db comma u, we have to maximize this value for each of the given node. So that is pretty much the question. For sample test case, you can read the problem statement given on the website. Below there are given some sample test cases with explanation as well, but we'll be focusing more on our own example, the diagram which you can see on the right hand side. We'll be seeing how to approach the solution using this same test case. The solution approach goes as follows. First, we have to root the given tree at the node A. So this comes as an intuition because uh, the input that is given to us in the question statement is just the tree. They haven't provided us the root. So we have to set a root by ourselves. So instead of setting a random node as a root, instead we set A as our root. So this gives us a benefit because in the expression that was dau comma dbu, I have written it as dax minus dbx. Just I have renamed u with x, but the benefit that I am getting here is that dax is now nothing but depth of the node x, because a is my root. So I have rooted my tree at A, that is the given node A, and now for any particular node X, let's say this is my node X because it's a special node. So what is dA comma X? So A comma X is nothing but the distance between these two nodes, and that is nothing but the depth of the node X. So rooting the tree at A helps us in solving the problem. Now let's further see what other concepts we can put in use to solve this question. So next we have to draw some paths from randomly choosing a node B, and we have to observe something. So for that, let me first choose a random node for B. So let's say this is my B node currently. So I have to pair it up with some special nodes. So I have three special nodes in my tree, that is F1, F2 and F3. So let's say I decide to pair it with F2. Then how are my distances going to look like? So the distance A comma X So the expression was a comma x minus d b comma x. So how is the path going to look like? dA comma x will look like this, that is all the way from F2 to A, because I have chosen F2 as my special node, and dB comma x will look like this. So from B to F2. So this is how the path will look like. So if you can observe in this diagram, the paths which are common in both of them are from F1 to F2, or to put in better words, from this green node to this F2 node. So what is this F1 node? Why is that node so special? So the node at that position is special because it is the least common ancestor. It is the LCA of B, F2. That is, it lies on the path from F2 to A as well as from the path B to A. So it is the least common ancestor of B and F2 in the given tree. Let's see one more example. Let's say that I choose this as my B node. So this is my B node. Now I need to pair it up with a special node. Let's say I pair it up with F1. So the path from B to F1 will look like this. That is, the distance will be along this path, and the distance from A to X, that is from A to F1, will look like this. Again, the common part over here, it goes from this node to this node. So this path is common. But again, what is special about this node, this orange node? The special point about this node is that it is the least common ancestor of F1, B. That is, it lies from on the path from F1 to the root and from B to the root. So if you try drawing many examples like this, take any node as your B node and any one of the special nodes and draw the paths between them. You will see that the common path is always between the least common ancestor and the special node. So this gives rise to an observation. Let's put it into better mathematical words. So the bigger picture here is that for any B, the general diagram of the tree can be represented simply in this manner. Like, there will be a node, that is current node B. Then there is a root over here, that is the node A. Then there is somewhere a special node, let's call that node X. And then in between there is somewhere the least common ancestor of B and X. So there will be some path from B to L, then from X to L, and then from A to L. So this is how the general diagram is going to look for any case or for any node B. So we can now redefine the expression that was given in the question. So now we know that A comma X distance is this red one. So from A to X is this red distance, and from B to X it is the green one. So if I have to redefine the expression dA comma x minus dB comma x in terms of L, then I can easily write it as dA comma L minus dB comma L, because the common distance x comma L is cancelled out. So the new expression that we have is dA comma L minus dB comma L, where L is some ancestor of B which has X in its subtree. So for any node, say B, L is some ancestor of B such that it has a special node in its subtree. Now there can be many such options for L. So which one should we choose so that our expression is maximized? So let's see how to choose the most optimal L. So now if we want to maximize this value, it means that dA comma L should be as big as possible and dB comma L should be as small as possible. So this means that L should be very close to B, or in other words, L should be the lowest ancestor of B, that is as close as possible to B. So we can define now L. What is L? By definition, now L is the lowest ancestor of B such that it has a special node in its subtree. And which is that special node? It is nothing but X. So now that we have defined everything in place, now the problem seems to be reformed. So earlier it was dA comma x minus dB comma x. From there we brought it to the ancestor L, and also we have now decided which ancestor we have to choose for any given B. So we have to choose the lowest ancestor such that it should have a special node in its subtree. That is the important condition over here. So that now gives rise to two more cases, and let's see what those cases are. The two cases or the two types are as follows. First one is type P, that is the nodes having special nodes in their subtree. So you can see on the left hand side in the diagram, this B node is of type P because there is a node X that is a special node in its subtree, somewhere in its subtree. But on the right hand side, you can see that this B node is of type Q because there are no special nodes in the subtree. So, but the ancestor, that is L, is a node of type P because L has X in its subtree, but but B does not have any special node in its subtree. So these are the two cases, and if we solve the question for these both cases, then we have solved it completely. The answer for first case, that is nodes of type P, is pretty simple because in that case the node itself is L. That is, this node is itself the lowest ancestor of B such that it has a special node in its subtree. So you can see that X is a node in the subtree of B. Therefore, B is nothing but its own lowest ancestor such that it has a special node in its subtree. So yeah, so in that case, our statement was d of a comma L minus d of b comma L. So this second one will get 0 in the first case. So the answer will be just the dA comma L. And we already know the distance from A, that is the root of the tree, to any node is nothing but the depth of the node. So in this case, the answer, that is the value of this expression, is nothing but depth of B itself. And now for the second case where B is of the type Q, in that case this statement still holds, but then the second part will not be 0 in that case. dB comma L will be some significant value. So we'll need to find both of these values, that is dA comma L, which is nothing but the depth that is easily known to us. Only thing that we need to calculate extra is this value, that is dB comma L, and that can be done using a second DFS. So let's see that how DFS helps us solve this problem. So we have actually seen the complete solution now. We went from the given initial problem to converting it to another statement, that is dA comma L comma minus dB comma L, and then we also decided a definition for L, that is L should be the lowest ancestor of B. Now we have divided that into two cases and we have solved it for both of them. Now the only part that remains is the implementation, and that is done using a depth first search or DFS. Let's see how. So the implementation will be something like this. So first of all, the tree will be rooted at A, so it will look like the diagram that you are seeing right now. And there are three special nodes given, that is F1, F2 and F3. So we know that we have defined P as the type nodes that have special nodes in their subtree. So first of all, in the first DFS, when we are doing the first DFS on the tree, we'll mark the special nodes, we'll mark the nodes as P or Q. So in this diagram, this node is of type P, then this one is of type P, P, P and P. Because if you have any special nodes, all the nodes along the path from that node to A will be of type P. So similarly, these three will also be of the type P. So all the P type nodes are marked. Now the remaining ones are definitely of the type Q. So I'll not write them, but I'll just mark their some of them, that is this is of type Q, Q and Q. So the answer for all the p-type nodes is pretty simple, that is the depth of the node itself. So whatever nodes that you are seeing with the mark p, the answer for them is nothing but their depth from A, that is the root. But what is the answer for all the q-type nodes? So the answer for all the q-type nodes is that, for example, if I take this left subtree, this smaller one, all the nodes in this subtree are of type Q. So they need to be paired with a X, that is a special node, and there will be a lowest ancestor L. So in that case, this node is going to be the lowest ancestor, this one. Let me mark this as L. So all of them will be paired with this L. So I can run a separate DFS for this orange subtree, this one, and find the distance from L to that node, because the statement was like d a comma L minus d b comma L. So for L, I directly know the distance from L to A, that is the depth of L. But distance b comma L, that I have to find, like let's say if this one was my node B and I have to find what is my this distance from B to L, then I need to run a separate DFS. So I will run a separate DFS for all such subtrees that contain only Q type nodes. So this is one subtree, then this one is another subtree, and this one here as well. So one DFS, the first DFS is for finding the depth of all nodes and marking the nodes that is type P or type Q, and the second one is for type Q nodes. So the both cases are handled and we know the answer for all of them. Also, while doing the first DFS, we also have to maintain or keep a track that for each P type node, which is the closest special node or the latest special node. For example, for this bottom node, this one, I'll point it with my mouse. So for this node, the closest special node is F2, but for the above node, while doing the DFS, for this one as well, the closest one will be F2. Then for the above one, it will be F1, and then for this one, it will be again F1. For this one, it is F3, then for above node, it will be again F3. So all the p-type nodes will know that which is my closest special node, because that will be paired with the q-type node. So let's say I am working on this B node, okay, this one which I am pointing with my mouse. So I have to pair it with some special node. So first I will look for the lowest common ancestor. That lowest common ancestor will be this one. And which one is the special node in the subtree? The special node is F3. So using my formula, I can calculate the distance. That is my one part of the answer. The distance will be dAl minus dBl. In that case, this one will be my L. This is my B and this is my A. And how to find the special node it is associated with or paired with? It is F3. So whatever was the value stored in this L, that is F3, that is nothing but paired with my current B. So in this manner, by using two DFS in order of n time, we can find the answer for the given question. Now the C++ implementation is as follows. For each test case, I take the input of n, k and a. I decrement a because I am going to follow zero based indexing in my tree at all times. Also, then I take the input for the special nodes, that is k special nodes, and then I mark them as special nodes, that is special is equals to true. Now once that is done, I take the input for my given tree. So u comma v, there is an edge between u comma v, so I do that by pushing them in an adjacency list. So adjacency of u dot pushback v and vice versa. Now I have my tree. Now I have to root it at the a node, that is my topmost node. So I do that by running a DFS, that is DFS of A. Now let's go to that DFS function. So the DFS function looks like this. in that DFS, first of all, for each node I mark its depth from the A node. So the depth of V is depth, and then I mark the parent as well. And then there's a special variable called as int sp is equals to -1. So what does sp do? Sp keeps a track whether there's a special node in my current node subtree. So if the value of sp is -1 even when the function ends, then it is propagated upwards. So in that way, I know which nodes are of type P and which nodes are of type Q, as discussed in the solution. So if the value of sp is -1 till the end, it means that that node is of type Q, or else it is of type P, as discussed earlier. So that is done. And so if it is not of type -1, it means that it is of type P. And for P type nodes, we know what is the answer. Answer is nothing but the depth of current node. So that's it. I just store the answer. Answer of V is nothing but depth of V, and I have paired it with which variable? So the value of sp is not -1. So what is it? So if the value of sp is not -1, it is the value that is the closest special node which is propagated to it. So that is the node X which my current node B is paired with. So I mark it as well. So actually you need to go through this function very carefully, pause the video, you'll understand what's happening over here, which information is propagated upwards, which information is not propagated, which condition is used to store the answer, and whatnot. So all this is done in the first DFS. Now once the first DFS is completed, we need to run the second DFS for type Q nodes. So coming back to the main function, after the routing is done, I again check for all nodes. So if answer of I is equal to -1, that is it is a type Q node and its parent is of type P. So you can see in our whiteboard also. So this node, this was of type Q and its parent was of type P. So we do the DFS, second DFS starting from this node, the one which I am pointing with my mouse. Similarly here also, this was of type Q and the parent is of type P. So we do a DFS from this node. So the DFS2 will be for that smaller subtree, and the condition for that is the current node must be of type P, the parent must not be -1, and the node of parent should not be equal to -1, which is essentially the parent should be of type P. So if all these conditions are satisfied, I do a DFS, second DFS, and in that second DFS, the answer for each node in that subtree, the smaller orange color subtree, is nothing but A comma L, that is answer of L, minus the current depth, that is D B comma L. So that I am storing over here, and everyone is paired with whatever is the answer of the L node. So that is done, and this DF is pretty small, nothing else, all was pre-calculated, and that's it. Once this is done, I have the answer for all nodes. So the answer of each node consists of two parts. First, the value of that statement, that is dA comma x minus dB comma x, that I'll output first for each node, and then any of the special nodes with which this answer was uh, given to me. So that was stored in the node array. So I just output that node of I plus 1. I am doing plus 1 because initially I had converted everything to 0 based, but the answer is expected in 1 based. So that completes the code. I know it can be confusing for many of you, but I'll be pasting the solution link in the comment. You can go over there, study the code. If you still have any doubt in any part, you can tag me in the comments and ask me specifically which part of the code you are not understanding. If you are familiar with DFS, this shouldn't be new to you. But if you are new to DFS, I first suggest that you learn DFS and then have a look at this code and try to understand. And if you are finding difficulty, where to learn DFS from, where to learn all these concepts, we have competitive programming tutorials or mini courses which are taught by our educators. You can learn all the concepts from here, and then you can go back to the question and solution. Also, if you want our plus subscription on Unacademy, you can opt for that too. You will get live classes, recorded sessions, practice problems, curated content for you, all at a reasonable price. And even in that, if you want a 10% discount, don't forget to use my referral code Darshan code 25.